Welcome to Economics 1723 Capital Markets, Lecture 3 module on risk and risk aversion. This is John Campbell. So today we just have this one topic, the modeling of risk, which again is foundational to the study of capital markets. So how do we model investor attitudes towards risk? We're going to start with the general model of microeconomics that you may have seen in EC 1010 or EC 1011, and then we're going to simplify in a series of steps. The general model of micro has many consumption goods. We're going to simplify to a single consumption good. So we're not really interested in the choices people make about how to spend their money. We're interested in their attitudes towards different investments. Now, of course, the real world has many time periods, but for now we're going to simplify to think about consumption one period from now. So we're going to imagine a world with only two periods, the present and the future, and all we're interested in is how much can we consume one period from now. That's really equivalent to caring only about how much wealth you have, since presumably at the end of the world you're going to consume what you've got. How can we represent preferences over wealth in different states tomorrow in the last period? Well, we're going to use the theory of expected utility of wealth, which I will explain in a minute. And finally, one can go even further, and we will do this a little later in the course. It's possible to assume a particular form for expected utility, which allows us to use the so-called mean variance analysis. And that's an influential method in finance that we will discuss in due course. Okay, so for now I'm going to explain the expected utility framework. We're going to assume that an investor has a utility function defined over wealth. We write it as U of W. We assume it's increasing. In other words, more wealth is better than less, and twice differentiable. So it has a first derivative and it has a second derivative. There are no jumps in utility and there are no kinks in utility. It's a smooth function. We're going to assume that when considering risky prospects, different risky investments, an investor is going to maximize the expectation of the utility of wealth. So this is the expected utility theory. So wealth is random. You control the randomness to some degree by choosing your investments, and you choose those investments in such a way as to obtain the highest value for the expectation of U of W. Now, what do I mean by expectation here? What does this letter E actually mean? Well, we're going to assume a world with a discrete number of states. Let's suppose there are two states. And these states have probabilities attached to them. Call the probability of the first state pi 1, the probability of the second state pi 2. Then an expectation is just a probability weighted average. Okay, so the expectation of the utility of wealth is a probability weighted average of the utilities of wealth in the two states. If in state 1 I have wealth W1 and in state 2 I have wealth W2, then the probability of getting wealth W1 is pi 1. I give a value U of W1 to that's the utility of wealth in that state. I multiply that by pi 1. Then I go to the second state, I have wealth W2, that gives me utility U of W2, I multiply that by pi 2. And then I add up across the states. That is what it means to say that we're calculating the expected utility of wealth. All right, so let's think about an investor in this world of two states. And let's suppose that the initial wealth of the investor is W0. And the investor is offered a gamble. The gamble is a coin toss that if you win, let's say it's heads, you get plus H, you get an extra H dollars. But on the other hand, if you lose, you have to give up H dollars. So the gamble pays plus H or minus H with probability 1/2. It's just a coin toss. So now, in the initial position, the investor has wealth W0 today, and if she turns down the gamble, she can stay with W0, whether it's a head or whether it's a tail. On the other hand, if she accepts the gamble, she's going to have W0 plus H, if she wins, and W0 minus H if she loses. An investor is risk averse. This is the definition of risk aversion. If she rejects this gamble that has a zero mean. Okay, so the average payoff is zero, and so this gamble is pure risk. There's no reward for taking the risk. So if you reject it, then we say you are averse to risk. You don't take risk for its own sake. You would only take it if you were paid to take it. Well, let's apply this expected utility theory. We're going to find that risk aversion puts some discipline on the utility function. And by that I mean it tells you something about what the utility function has to look like. Okay, so the investor is going to reject the gamble that I just showed you on the previous slide if the utility of wealth W0 for sure is bigger than the expected utility of taking the gamble. What is the expected utility of taking the gamble? It's 1/2 utility if you win plus 1/2 utility if you lose. And so the investor will compare the expected utility of gambling with the expected utility, which is actually the known utility of not gambling. And risk aversion means that the left-hand side is bigger than the right-hand side. Now, we can multiply this equation by 2 and rearrange terms. And we're going to find that u of W0 minus u of W0 minus h is greater than u of W0 plus h minus u of W0. What's the interpretation? On the left, we have the, you could call this the pain of losing. This is the utility difference between staying where you are and losing. So call this the pain of losing. On the right, you have the pleasure of winning. This is the difference between the utility if you win and the utility if you stay where you are. So risk aversion, very intuitively, just means that the pain of losing is greater than the pleasure of winning. Now, in general, you'd have to adjust for the probabilities of those two things, but in this example, I've chosen the probabilities to be equal. That's why the 1/2s disappear when I multiply through by 2. Okay, so for the investor to be risk averse, the utility function must satisfy this inequality, that the pain of losing exceeds the pleasure of winning. So let's draw the utility function now. And what we're going to see is that risk aversion implies a concave utility function. Concave means that the function is curving downwards. So this curve here always lies above a straight line drawn between any 2 points on the curve. So I can take a point here and a point here. I can draw a line between them, a straight line, and the curve of the utility function is always above that straight line. Now, why does risk aversion imply a concave utility function? Well, on the horizontal axis, I've plotted the initial wealth, the wealth if you win, and the wealth if you lose. Then for each level of wealth, I calculate the corresponding level of utility by going up to this curve and then across to the vertical axis. What you can see is that this vertical distance here is the pleasure of winning, and this vertical distance here is the pain of losing. And risk aversion means that the pain, this distance, exceeds the pleasure, this distance. So if we let the amount being gambled shrink to 0, we're going to move all of these vertical lines closer and closer to one another. What we're going to find is that the marginal utility falls as wealth increases. In other words, u prime of w, the first derivative of the utility function, is declining or falling with wealth. Okay, you can see that the slope of the utility function at each point is declining. The curve is flattening out as we move up. Well, if the first derivative is falling with w, that means that the second derivative, which we write u double prime of w, is negative. And a function with a positive first derivative and a negative second derivative is a concave function. Final topic for today is how we measure risk aversion. We want to know not only is a person risk averse, but how risk averse are they? And for this, we're going to look at the magnitude of this second derivative. Remember, we just said the second derivative being negative is what defines risk aversion. So we want to look at the magnitude of that, or equivalently the rate at which u prime falls with w. But we have to do it in a way that is invariant to units of measurement, because utility has no natural units. There's no such thing as a util in which we measure utility. So we have to scale so that units of measurement don't matter. And the first and most obvious way to do that is called absolute risk aversion. We take the second derivative, we flip the sign. We put a minus sign here. We flip the sign because, of course, the second derivative is negative and we're measuring risk aversion. So we change it to a positive number. And then we divide by the first derivative. And the division by the first derivative makes this thing invariant to units of measurement. There's also a concept called risk tolerance, which is the reciprocal or inverse of absolute risk aversion. And then finally, there's a concept called relative risk aversion, which just multiplies absolute risk aversion by wealth, or normalizes absolute risk aversion with wealth. So relative risk aversion is wealth times absolute risk aversion. And we'll see as we go on in the course how useful these concepts actually are. Finally, I want to mention that academic economists commonly use certain parametric forms for the utility function which are convenient and help us do analysis. So let me run you through these examples. The first example is linear utility. U of w equals some constant a plus some slope coefficient b times wealth. Now, this is risk neutral because if we calculate absolute risk aversion for this utility function, it's going to be 0. The first derivative here is b, the second derivative is 0, so absolute risk aversion is minus 0 divided by b, which is 0. Quadratic utility, u of w equals a plus bw minus cw squared. That's convenient for some applications, but it's problematic for various reasons. One is that as wealth increases, if you look at this function, it's going to have a maximum. At some point it's going to curve over and you're going to reach the bliss point where you're so blissed out that further wealth is actually harmful to you. And as we've observed human behavior over the years and the decades and the centuries, we never seem to reach that bliss point. So that's a problematic feature of quadratic utility. I should also mention that this quadratic utility function has absolute risk aversion, which increases with the level of wealth. And as we'll see later, absolute risk aversion says how much you would pay in dollars to avoid a given absolute risk. It's a little weird to think that Bill Gates would pay more than you would to avoid a given absolute risk, but that's what quadratic utility would imply. Another functional form is called exponential utility, or if we're being very precise, negative exponential utility. We write it u of w equals minus e to the minus aw, minus the exponential of minus aw. And if you take the derivatives, that's got constant absolute risk aversion because a of w is the absolute risk aversion function is just this little a, this exponent here. Then there's power utility, which looks like this. U of w equals w to the power 1 minus gamma, minus 1 divided by 1 minus gamma. That's got constant relative risk aversion because absolute risk aversion is gamma divided by wealth. Again, if you take the derivatives, you'll see that. And then relative risk aversion is wealth times absolute risk aversion, so that's going to be just gamma, this power coefficient gamma. A special case of this is log utility. U of w equals the natural logarithm of wealth, which implies that relative risk aversion is 1. Now, you can see that looking up here, if we set a gamma equals 1, we've got, and we take this literally, we've got 0 divided by 0. So obviously, to handle that case, as gamma goes to 1, you have to take the limit appropriately, and if you do that, you get u of w equals log w. So log utility is another very important special case. Again, as we go on in the course, we will use some of these special cases, and we'll see that they can give us insights. And we're going to do an exercise in class where we ask ourselves, each of us can ask ourselves how risk averse we actually are by doing some thought experiments. So I hope you've enjoyed this introduction to risk aversion, and I look forward to seeing you in lecture.